Okay, so in this unit, much like we did a lot of in grade 10, applied and pre-calculus, we looked at linear relationships. But we're going to look more like, we're going to do more real life stuff with it. Like we just, in grade 10, we did a lot of generic XY graphs where we found the equation of them. Here we're going to actually use real examples to work with linear relationships and to make predictions, which is a big part of what linear relationships are. They help us make predictions about things, okay? Which is something that we often want to do. So an example, you know, relation between the number of hours you work and your gross pay. Okay, there's just one example of a linear relationship. As one goes up, the other one goes up by a corresponding amount, depending on how much you get paid per hour, if you're getting paid per hour. We've already seen in Unit 2 where we use graphs to show relationships between two variables, okay? When we are working with linear relationships, we can use line graphs, which are very similar to what scatterplots are. But we're going to focus on scatterplots right now. And you can see here a scatterplot is a graph with points that represent specific data. So it's, you plot points, and then you can connect the points or not connect the points, depending on whether the data is continuous or discrete, which is another thing that we talked about in the second unit. So a lot of this, it's a new type of graph, but it's very similar to a line graph. And we still use discrete and continuous data, and how we create the graph is very similar to how we created the others. We need a title, we need labels for each of the axes, the horizontal axis where the independent variable is, and we talked about what an independent variable was before. The vertical axis where the dependent variable is, and we talked about what the dependent variable is before, so you can see I've just revisited the definitions there. Okay, and then of course we need to plot the points, okay? And depending on what we do with those points, we may connect them, we may not connect them, or we may have to find a line that sort of best fits it. Okay, which is something that we do from scatterplots, which you would remember from statistics. Okay, these ones I actually want to do, okay, by hand, because they don't take very long. It is possible to do it by Excel, like we did with the other graphs. You would just choose an XY scatter plot, and then your title, your labels for your vertices, enter all your data, and you would get a similar graph. But with this one, I just like to actually do a couple. Okay, so here we've got age in years compared to height. So the first thing we want to do when we make the scatter plot is we want a title. So we could just say ages compared to heights. We have to determine which one's the independent variable and which one's the dependent variable. Well, I suppose you could either one, because if you're, I mean, usually height would depend on your age, okay? Whereas age doesn't so much depend on your height. So we'll use age as the independent variable and height as the dependent variable. So we'll just do this. And we'll do this. And we said that height in centimeters is going to be our dependent. Age in years. So now we got to choose the scale. Starting 0 at both axes. Look at the age. Look at all the numbers for the age. I think it should be pretty obvious to you what we should go up by. What should be our scale? Come on. What? 10. Thank you. So 10, 20, 30, 40, 50. I don't think I need to go. Yeah, 50 was the highest, so I usually just go one more. Now the height's a little different because we want to start at 0, but if you look at all the numbers, the smallest height is 142, and the tallest height looks to be 178. Well, I mean, I suppose you could go up by 5 starting from 0, but you'd be going up a long way before you start plotting any. Just a second. Yep, I want you to answer that. I just want to say, like, if we started at 0 and went up by 5s or something, or we went up by 10s, we wouldn't be plotting a lot down here. It'd be all up here. There is a way to get around it.
I don't know what it's called, but there's like this swoopy thing on the y-axis, and then you kind of shows that you skip a certain range.
Right. So, and the math term we can use for that is we truncate it. So what we're going to do is we would kind of draw it like this. That means that we're kind of scrunching the vertical axis, saying that we're still starting at 0, but really nothing much happens until we get to 140 and above, because the lowest value is 142. So I'd be plotting nothing down here. It would all be up here. And that allows me to make a smaller scale, which allows me to be a little bit more accurate with my graph. But keep in mind, there's a big space below there. So this way, what am I going up from? The highest is 180. So I could go up by 10s, 150, 160, 170, and 180. If I tried to go up by 5s, I don't think I'd have enough. And now we just want to plot the points as best as we can. And I'm just, instead of me scrolling back and forth, I'm just going to get okay, so we've got 50, 162, which is somewhere around there. 10, 152, which is somewhere around there. 20, 173, which is somewhere around there. 30, 147, which is around there. 20, 163, which is around there. 40, 168, which is around there. 50, 178, which is around there. 10, 142, which is around there. 30, 162, 40, 178. Yeah, I'll be in line with that one. And 10, 147. Should be around there. Now, is this relationship linear? No, and the best way to answer that, remember, linear contains the word line. So when you're looking at a scatter plot, can you draw like a straight line through all the points? No, you can't. Okay, and connecting all the points would be a useless exercise, even though technically age and height would be continuous variables. Okay, we'll talk about something that we can do with scatter plots a little bit later. Okay, many times we'll get linear or very close to linear, but in a way, this is kind of linear because it does sort of go like that. The question is, so we could actually put a line in to help us make predictions between age and height. But we'll talk about that a little bit later. But that's essentially what a scatter plot looks like. Okay? We'll look at ones that are way more linear than these ones. But something to keep in mind, and again, we reviewed it, we did this in Unit 2. How do we know when to connect points when we're doing a scatter plot? And actually, it's almost like you're turning it into a line graph. It depends on the type of data. Discrete data, we talked about before, are things that you can count, like people, objects. You don't have decimals or fractions. You can't have 1.6 of a person. You can't have 2.5 of a desk. So it's things that we can count. Whenever one of the variables is discrete data, we never connect the points. They both have to be continuous, which means we can have fractions and decimals. And we talked about examples, okay? Age, height, weight, distance, time. All of those are continuous because I can write fractions of time, fractions of weight, fractions of height, fractions of distance. Okay? So continuous data is what we can measure. Discrete is what we can count. So we're going to look at one more graph, which is basically going to look like a line graph this time. So here we have another example with Goldilocks. Yes, very clever. Hates it when she burns her mouth on hot chocolate in winter, but she also doesn't like to drink it too cold. So she decides to conduct an experiment to find out how long she should wait before she drinks her hot chocolate, so it's not too hot or too cold. We want to draw a graph of this data. So we set it up the same way. Just make sure you have everything out. Title, labels for axes, proper scale, and then points. And then we have to also determine, can we connect them? Okay. Well, here, look at the two variables. Is time continuous? Could I have fractions of time? Yes. Is temperature continuous? Yes. So they're both continuous. So I should be, if it forms a line, I can draw a line. If it forms a rough line, that's when I'm going to have to draw what's called a line of best fit, which we'll talk about a little bit later. So we could say what? Time compared to hot chocolate temperature. Hot chocolate temp. And so we would have temperature as the vertical axis in degrees Celsius. We would have time in minutes, thank you. Time in minutes. That's the horizontal axis where the independent variable is. We want to start at 0 for both of them. We may have to truncate or put a squiggly in for the vertical axis from 0, or we may not. What do you want to go up by for time? 5? Seems to make sense. Considering that 4 of them are multiples of 5. 25, 30. The lowest y is 74. So we could probably just, highest is 100. Do I have enough to go up? I could go up by 10s, or I could go up by 20s. I think if I went up by 10s, I wouldn't have quite enough. Or you could put a squiggly in and started at 70 and gone up by 10s. It's still correct. So our points are 0, 100. I'll use a different color. 0, 100, 199, 595, that's 90, 1090, pretty linear so far. 15, oh, sorry, I forgot to correct that. No, I did correct it on yours, isn't it? Does it say 10, 90? Okay, good. Because I had the wrong one in there before. 1585, 1783, and 2674. There's 70, 74. 26 is about there. That's pretty linear. So in this case, we would connect the points. Connect points. Because both variables are continuous. If, like, it doesn't have to be perfectly linear in order to draw a line through the data. And we'll talk about that a little bit later when we take an example like the first scatter plot we did and figure out how to draw a line through the points. We're not going to be able to get all the points, but if we can sort of roughly average the points above and below, then we can use that line. And finally, just want to talk about anticipating graphs. How can we predict the shape of graphs given the situation? So here's 4 situations and 4 graphs. You need to match each situation to the most suitable graph. The height of a ball at the top of each bounce after it's been dropped. First, second, third, or fourth. So you're measuring, you drop a ball, and then you're measuring its height after every bounce. This one? So that means that the ball bounces low and then it starts bouncing higher and higher and higher, and then it starts bouncing lower and lower and lower again. I think it would be the third. Because if you think about it, if you drop a ball, it bounces to a certain height, comes back down and bounces to a little bit less. A little bit less, a little bit less, a little bit less. So it's high, little less, little less, little less. So this would be A. The speed when you ski down a valley and come up the other side. Second one, right? Because as you come down, your speed increases, but when you start to go up the other side of the valley, your speed decreases. The amount of money you earn compared to the hours that you work. Assume you get paid by the hour. The what? The fourth one. You don't work, you don't get paid. And you always get paid a constant amount. So it goes up by a linear amount. And then this, the value of an investment with interest compounded annually, that's important. If it was simple interest, it would be linear. Okay? Because it's compound interest and the interest grows on interest, it takes a curve and shoots up quicker. Just something to keep in mind. Okay? Okay.